Hello everyone. I am making this video for myself and to anyone who may be watching it in the future. And what I'm going to do is explain two of my projects. First is differential equation solver that I made, and second one for the n-body problem in gravitation. Now, to solve the n-body problem, I needed to solve this problem about differential equations or motions. So let's start with the premise. The premise is very simple. The premise is this: you have this some coordinate axis, and all of our motion is going to happen on this axis. Like it can go anywhere here. This particle right here. Now the acceleration or the force acting on this particle, I'm just going to write acceleration, is a function of its position and velocity, where it is, and how fast it is moving. Is function of these two things. Like in spring or in many other systems, you can find many examples where the acceleration is dependent on position and the velocity of the particle. So the equation we model is something like this: the second time derivative of position is a function of position and the first time derivative of the position, which is velocity. Now sometimes you can solve this equation and sometimes you cannot solve this equation analytically. Now to solve any equation, whether it can be solved analytically or not, we can solve any equation numerically. And what I mean by numerically is we can chop up the whole motion in very little parts, spaced by equal time intervals. Like these spaces are not equal or might not be equal, but the time intervals are equal. For example, I analyze the particle's position at time t equals to 0, the initial position and the initial velocity. Then I observe the particle's new position and velocity after a time 0.1 second, then again after a time 0.1 second, then again after a time 0.1 second. And by doing so, these positions and the velocities associated with each position might not be equally spaced, but these time intervals are equally spaced. The position and velocities are observed at equal time intervals, after equal time intervals, say 0.1 second or 0.01 second. So by doing this again and again and again, we can know the whole motion. We can describe the whole motion or predict the motion at a future time. So how to do this? The first thing is we observe that we know two initial conditions. First is the initial velocity and second is the initial position. By using these two, we can know initial acceleration, right? And by using this initial acceleration, we can calculate the new position, right? The new position we can calculate, and by using that new position, we can calculate new velocity or vice versa. And just there is this interplay between acceleration, velocity, and this acceleration, velocity, and position. And by doing this again and again and again, we doing this in a loop many times, we can describe the whole motion. We can describe the position at any point. We can describe the by point I mean at any time. We can describe the velocity at any time. We can describe the acceleration at any time. So these are the equations. The velocity at a time at any time t plus this small time interval e divided by 2. What I mean is, for example, we are taking 0.1 second as a equally spaced time interval. So we want to calculate the velocity at some point like 2 seconds and plus 0.5 seconds, like 2.5 seconds. So we can know this velocity. We can know this how would we calculate this one? We can calculate it by using the information about velocity at a time interval equally spaced before that time, like t minus e by 2. Like using the velocity at t equals to 1.5 seconds, we can calculate v at t.25 seconds. Now these are not equal. We are going to add another time, another velocity term. We multiply it, we add something, and that something is this time interval epsilon, and the acceleration at the time t, acceleration in the middle of these two velocities. By middle I mean at the middle time interval, at the middle time. So so we can calculate the new velocity by using the old velocity, right? And by using this new velocity, we can find the new position at t plus this time interval e, by using the position at the old time interval and adding this e again this epsilon naught times the velocity at this new position, t plus e. So this is the t plus e by 2. So to calculate the new position, to calculate any new position like this one, we need velocity at this midpoint, not this midpoint as a spatial midpoint, spatial like in space, not this midpoint but the midpoint in between the time intervals, like e at e by 2. And using the position at this position, the old position, we can know the new position. Now to know this v, we can use the acceleration, we can use acceleration, this acceleration and the initial v, like to calculate. Wait, let me do this. These are 2 points. To calculate v here, we use v here and v here, this one, and acceleration here, this one. And to calculate this acceleration, we use the positions here and velocity here. Like you know the definition of the acceleration, right? It's a function of position and velocity. So you use old positions and velocity to calculate new acceleration. You use this new acceleration to calculate new velocity, and you use this new velocity to calculate new position, and then you use this new position and new velocity to calculate new acceleration, and then you use this new acceleration to calculate again further new velocity by using the old velocity also mixed in this expression. And this whole loop just goes on and goes on to calculate the positions, velocities and acceleration at new times. So this was the whole solution. So let me just show you the program. Here is the program. This is the different coordinate points. I defined this function as coordinate points because it's calculating the coordinates, and it's taking total time as its argument, initial value of position, initial value is velocity, and this e is a small time interval like 0.01. And there is this expression. Now this expression is a string, which is the expression for acceleration. Like here I'm using this expression to evaluate, I'm using this expression and evaluating it to calculate a. And then there is just this looping for a total time interval t by going over and over and over on small time intervals and calculating new v's, new x's and new t's, and then new accelerations every time. Wait a second. So what I did is to plot a function, right? I set the acceleration as this, the expression is this, the sin x plus cos v. Basically this is my premise. So I'm solving this differential equation, like the position of the particle is x at any time, the velocity of the particle v, and the acceleration of this particle is sine of this x and plus cosine of this position v. So basically I'm solving this differential equation, that second time derivative of position is a function of sine of the position plus cosine of the velocity, which is the first derivative of position with respect to time. So solving this differential equation is, I don't know if there is a method analytically to solve this equation because I'm just I'm in first year right now, but I do know that I can solve this numerically by my program right here. I just have to give what I'm doing essentially is I'm solving this differential equation. What do I mean is I'm solving for the positions and the times and for the motion of such a body that is moving with this acceleration. So for a total time of 10 seconds or 10.1 seconds, for a total time of 10 seconds, and the expression being this, I'm plotting t versus the x of t, that x is a function of t, this graph, and you can see that here is the graph. So as t goes on, the position changes, and the position changes like this, and I can predict t at any time. For example, I initialize it with the initial positions of what are the initial position I chose. Initial x is 2, that is it's at a distance of 2 meter from the origin, and the initial velocity was 0, right? So this is the whole motion. I can predict the time, I can predict the position at any time, like at time 8.5 seconds the position will be 12.51. I'm seeing this from the bottom right corner. So this is the thing. I can change this expression to anything. For example, if I want to solve the equation for simple harmonic motion, I can change this expression to negative 4x, 4 being the omega square term in the simple harmonic motion. So it is basically a particle moving in a simple harmonic motion with an angular frequency of 2. And I change this expression, so I am expecting. And what are the initial conditions? The initial conditions are initial x is 2, so basically I have stretched that spring to 2 meters or whatever, 2 centimeters, whatever you want to call it, and I didn't give it any initial velocity, so I just stretched it by 2 meters, and then I just leave the system to do its thing. And here is this, as expected, a cosine graph. So it goes down, it goes up, it goes down, it goes up, like this, a cosine graph. Now, so this is the differential equation solver. You can put any expression here, as long now I am using the numpy module as np. So make sure if you are using some square root or cosine, you put them as np dot, or you are using some power, you use numpy module as np, so that you don't get an error. So you can put any expression, you can put any acceleration, and you will get the positions and velocities and everything. Now I have not shown the velocity, but I can make a list for velocity and add all these velocities in that to know the velocities at every position. Now moving on to the n-body problem. For the why I did this whole thing to solve the n-body problem. So to start with the n-body problem, first let's take two problems, two bodies. So solving for two bodies is analytically possible, and to know the motion of three bodies in under gravitation is not really simple, because motion is really chaotic, and many people say it's impossible to guess or impossible to know analytically what's the solution of three body problem is, but you can solve it numerically. So let's start with two bodies. Let's say you know that there are two bodies in space. You know their initial positions, like one is kept here, one is kept here. You know their initial velocities, like one is going there, one is going there. Now how did the system evolve? So I'm just using the same premise. I know the initial x, y, and z's of the bodies. The first body, and I know the initial x, y, z's of the second bodies, the positions of the second body. So I know these 6 quantities, and I know the initial velocities and x component of that velocity, y component of the velocity, z component of the velocity for the first body, and similarly for the second body. So I am given with this 3 plus 3 plus 3 plus 3, that are 12 conditions, 12 initial conditions. So by using these 12 conditions, I can calculate I can calculate accelerations, and now that acceleration would be a function of x, y, z, the x component of that acceleration, the y component of the acceleration, the z component of that acceleration, and similarly for this body, x component, y component, and z component. Now these acceleration will depend on these according to gravitation, and also for this. After calculating this acceleration, I can know the new velocity, and by using that new velocity, I can know the new position, and by using this new position, I can calculate further new accelerations, then further new velocity, and further new positions, and by continuing on in the same manner, I can predict the whole motion of the system, right? Whatever it might be, it may not be like this, but whatever it may be. So what I did there for one equation, I am going to do this for a total of 6 equations, like for ax, ay, az, ax, ay, az for the second body, and I will know the 6 positions, like x position, y position, z position of the first body, and same for the second body. And by doing that, I have essentially solved the two body problem of gravitation. I can do this for the 3 body problem. Just the number of equations will increase, and I will have to add 3 more equations, so total 9 equations for these. And by doing further and further, I can solve any n body problem with given the appropriate amount of initial conditions, and I have to do a lot of calculation, but it can be done, right? So here's the algorithm for two body problem. This function is for acceleration. I'm calculating the x coordinate of the acceleration, the y component of the acceleration and the z component of the acceleration by using the formula for acceleration in gravity. These are the initial vectors, the initial positions and initial velocity, and then all that things which were done for only one body, like it was done one times. Each of these things are done six times, like three times for first body, three times for second body, three times for first body, three times for second body, and everything else is just same. And then last में I have plotted all these. So for a body, so this what's this? This is for this one, like there is this xy plane and there is this body here, there is body at origin. One body I have given the initial velocity in the xy plane, and for another one I have given the initial velocity in the z direction. And how would this system evolve over time, like something like this? I don't know what's the exact shape would be, but this graph right here is showing that. So you see the body started moving. The first one is the blue body, which is the more massive body, and it's moving upwards in the z-axis. And this red body, which is relatively lighter, is moving in spirals, elliptical spirals around this first body, and the system is evolving like this.